Hello, this tutorial is about survival analysis. This tutorial will cover 6 main points. First of all, we are going to learn what survival analysis is. Then we will look into what sensor data are. We will learn survival and hazard probabilities and learn how to calculate these values in the third point. After this, we will learn methods we use to perform survival analysis, including Kaplan-Meier plot, log-rank test, and Cox regression through an example. Before we start, I would like to introduce to you two good reference books. The first book is Survival Analysis, a self-learning text written by David G. 𝗙𝗏𝗏 and Mitchell Klein. The second book is Medical Statistics for Beginners, written by Ramakrishna. I found these two books are very useful, and I think they could be a good references for you. Now let's start with what survival analysis is. In this section, we will focus on the definition of survival analysis and the terms survival time and event of interest. So, what is survival analysis? Survival analysis, or more in general, time to event analysis, is a group of statistical methods used for data analysis where the outcome variable of interest, time, until an event of interest occurs. The start here means start follow-up. The time can be measured in days, weeks, months, or years. An event can be death, disease, relapse, or recovery. Although it is called survival analysis, but it does not always mean the analysis of survival time. The analysis can be the time of recovery after achievement, or the time of relapse after a rehabilitation. For example, you may be interested in analysis of time until death after a disease was diagnosed. This truly means survival analysis. However, if you want to investigate the time until the recovery of an illness after achievement, it is not the analysis of survival time, but recovery time. Survival analysis can also be used to analyze the effect of a factor or several factors on the time until an event of interest occurs. For example, you may want to investigate the effect of treatment methods on the time until the recovery of an illness after treatment. Or you may be interested in examining the effect of pesticide types on the survival time of an insect. To now, you know what survival analysis is. Next section, we will learn an important aspect of survival analysis, that is sensor data. This video is about sensor data. In this section, we will focus on what sensor data are and why we have sensor data. When you collect data for performing survival analysis, you will know time until the event occurs for observations. However, some observations you may do not know when the event of interest occurs. However, it is still useful when you have that data for the analysis. These data types are called sensor data. Why censoring occurs? A censoring can occur when a person does not experience the event before the study ends. For example, in these cases, or a person is lost to follow up during the study period. For example, this case. Another reason of censoring is a person withdrawing from the study because of the death. If the death is not the event of interest, or other reasons such as adverse drug reaction. For example, Z is a withdrawal patient. In this study, there are 6 persons, and we know the time until the event occurs for person A and F, and this is a person A and F. And you can see cross is a symbol to show event occurs. However, we do not know exactly the time until the event occurs for the person B, C, D, and E. So the data from these persons are censored data. The censored data are labeled as 0, while the data that we know the time until the event occurs are labeled as 1. So the data above can be arranged in this table. After you collect data, you can perform survival analysis use a set of methods including Kaplan-Meier estimate or KM estimate, log-rank test, and Cox regression. Survival analysis is based on survival probability and hazard probability. So before we dig deep into the methods of survival analysis, we will learn these terms. This tutorial is about survival function and hazard function. In this tutorial, we will delve into survival probability or survival function and hazard probability, or we can call hazard rate or hazard function. Then we'll look at types of hazard curves. After this, you will find out the differences between survival probability and hazard probability, as well as their relationship. In the last section, you will delve into the cumulative hazard. So, what is survival probability? The survival probability or hazard function, denoted by St, is a probability that a person survives longer than some specified time. The survival probability St can be described as this equation, in which P stands for probability, capital T is the random variable for a person's survival time, and small letter t is any specific value of interest for the random variable capital T. For example, if you want to evaluate whether a person survived longer than 5 years after undergoing a treatment, small t equals 5. And then we asked whether capital T exceeds 5. This is the function to calculate survival probability at a given time. In this equation, Stj is the probability of being alive at time Tj. Stj minus 1 is the probability of being alive at time Tj minus 1. Nj is the number of patients alive just before Tj, and Dj is the number of events at time Tj. At time T0 equals 0, the survival probability S0 equals 1. The value of St is constant between times of events. Therefore, the estimated probability is a step function that changes value only at the time of each event. We can easily see that in the Kaplan-Meier curve. This is the Kaplan-Meier curve that describes survival probability versus survival time. We can see the survival probability is the step function, and the probability is constant between events. We will look further into this curve and learn how to calculate survival probability through an example in the Kaplan-Meier estimate. Survival probability focuses on not failing or not occurring, while hazard probability, denoted by Ht or lambda t, is defined as the rate of failure or event occurs at a given time, given that the failure has not occurred prior to time t. In other words, the hazard probability gives the instantaneous potential of having an event at a time, given that the individual has survived up to that time. To get an idea of what instantaneous potential means, we consider the concept of velocity. For example, if you are driving in your car and you see that your speedometer is showing 60 km per hour, what does this reading mean? It means that if you continue to drive at this speed in the next hour, you would cover 60 km. This reading gives the potential at the moment you have looked at your speedometer for how many kilometers you will travel in the next hour. However, because you may slow down or speed up or even stop during the next hour, the reading of 60 km per hour does not tell you the number of kilometers you really will cover in the next hour. The speedometer tells you only how fast you are going at a given moment. That is, the instrument gives instantaneous potential or velocity. This is a survival function in which capital T is the random variable for a person's survival time. Small letter t is any specific value of interest for the random variable capital T. Delta t denotes small interval of time. The probability in the numerator of hazard probability is conditional probability. It is the probability that a person's survival time, capital T, will lie in the time interval between t and t plus delta t, given that the survival time is greater or equal to t. The hazard function is sometimes called a conditional failure rate. It is probability per unit of time. It is the rate but not the probability. The rate ranges from 0 to positive infinity. Hazard function is instantaneous potential per unit of time, and lim or limit gives instantaneous potential. In contrast to survival curve, hazard curves do not start at 1 and go down to 0. It can start anywhere and go up and down in any direction over time. Hazard rate is always greater or equal to 0 and has no upper bound. Here are some graphs showing different types of hazard curves. The first graph shows a constant hazard for a study of healthy persons. For a person who continues to be healthy throughout the study period, his or her hazard rate for being ill at any time remains constant throughout the following up period. The second graph shows a hazard function that is increasing over time. An example of this kind of graph is called an increasing 𝗷𝗡 model. Such a graph might be expected for leukemia patients not responding to treatment, where the event of interest is death. As survival time increases for such a patient, and as the prognosis accordingly worsens, the patient's potential for dying of the disease also increases. In the third graph, the hazard function is decreasing over time. An example of this graph type is called a decreasing 𝗷𝗡. A graph like this might be expected when a person recovering from a surgery where the event of interest is death. The hazard probability decreases because the potential for dying after surgery usually decreases as the time after surgery increases. The fourth graph shows a hazard function that is first increasing and then decreasing. An example of this graph type is a log normal survival model. We might expect such a graph for tuberculosis patients because their potential for dying increases early in the disease and decreases later. So, We have learned what are survival probability and hazard probability and their properties. We know they have differences, and here are the main differences between them. The survival function focuses on not failing or not occurring, while the hazard function focuses on occurring. Regarding data analysis, the survival function is more naturally appealing for the analysis of survival data because it directly describes the survival experience of a study cohort. However, the hazard function is interested in a measure of instantaneous potential for occurrence of an event. It may also be used to identify specific model form, such as an exponential, a 𝗲𝗏, or a log normal curve that fits one's data. Besides, the hazard function is a math model for survival analysis. Survival probability ranges from 0 to 1, while hazard rate varies from 0 to positive infinity. Although there are differences between the survival function and hazard function, there is a clearly defined relationship between these two functions. This is the equation of the relationship. The equation shows hazard function equals minus derivative to time multiplied by the natural logarithm of the survival function. Probably we need a separate tutorial to explore why we have this equation later. The point here is that if either survival probability or hazard probability is known, the other is automatically determined. Unlike survival probability, there is no simple way to estimate hazard rate. Instead, a quantity called the cumulative hazard, denoted by capital HT, is commonly used. It is defined as the integral of the hazard, or the area under hazard function between times 0 to t. Mathematically, the cumulative hazard function equals minus natural logarithm of the survival function. This is a cumulative hazard curve. The cumulative hazard increases as the time increases. The cumulative hazard is used to characterize the accumulated risk of experiencing the event of interest up to time t, and this function is an intermediary measure to estimate hazard rate. Up to now, you have understood what is survival analysis, sensor data, and two important terms, survival function and hazard rate. In the next section, you will learn the Kaplan-Meier estimate, a method we can use to visualize the survival probability or survival function. I see you in the next tutorial. Thank you. This tutorial is about Kaplan-Meier estimate or Kaplan-Meier curve. In this tutorial, we will cover what Kaplan-Meier estimate or KM estimate is and what it is used for. Then we will delve into how to calculate survival probability from an example. In the last section, we will plot and interpret the meaning of KM estimate. So, what is Kaplan-Meier or KM estimate? KM estimate is a curve that describes the survival probability versus time. These curves can help us easily to see the survival probability of a patient group or different patient groups. So, the first role of KM estimate is to visualize the survival probability of survival data from a study cohort. Secondly, it can be used to compare the distribution of survival probabilities between two treatments or more than two treatments. You also can estimate the median survival time, that is the length of time in which half a patient dies. The KM curve is a survival probability curve. So, first of all, we will calculate the survival probability through an example. This example investigates the effect of two treatments on the survival time of a group of patients with a disease. This is the data of the study. The first column is the patient number, and the second column is the time of events. The next column is the event of interest, including died, survived, or unknown. The last column is the treatment method, and there are two treatment methods, 1 and 2. The data are summarized in this table. As you can see, treatment 1 had 4 patients die and 3 patients were censored, making up a total of 7. The treatment 2 had 6 patients die and 2 patients were censored, making up a total of 8. The censored data are unknown or survived data, as you can see here. There are 2 treatment groups, so we will calculate survival probability for each treatment. This table shows how to calculate survival probability for treatment 1. Treatment 1 has 6 patients listed in the column 1. The column 2 is the survival time and the plus sign mean censored data. The next column is the number of patients alive, and the fourth column is the number of patients died. The last column shows how we calculate the survival probability. As you can see, at the time 0, the survival probability equals 1. At day 8, the survival probability is calculated by multiplying the survival probability at time 0, that is 1, with 1 minus 1/7. 1 here is the number of patients died at the day 8, and 7 is the number of patients alive at day 8. At day 12, the survival probability is calculated by multiplying the survival probability at day 8 with 1 minus 1/6. 1 here is the number of patients died at day 12, and 6 is the number of patients alive at day 12. Because no death record for censored data, so the survival probabilities on day 15 and day 25 similar to that on the day 12, and we leave them blank. You can easily calculate the survival probability of day 37 and 55 as you did on the day 8 and day 12. We leave the blank for the day 72 because it is a censored data. As you can see, the survival probability reduces as the time increases. Similar to treatment 1, you can calculate survival probability at the time point where the event occurs for treatment 2, and these are the result of calculation for treatment 2. After the survival probabilities of 2 treatments were calculated, they can be visualized by using KM curve. The KM curve can be drawn using statistical software such as R, Python, or SPSS. These graphs are step curves, and you also can see the sensor data as plus signs. It can be seen that probabilities at sensor time point are similar to the probability of previous events. For example, this is the previous event of these 2 sensor data. After you have KM curve, you need to interpret the meaning of results. In this study, KM estimates show treatment 1 has higher survival probability than treatment 2. The median survival time, or the length of time in which half a patient died for treatment 1, is 37, while this value of treatment 2 is 5. That means more patients survive in treatment 1 than treatment 2. The Kaplan-Meier curve can give you an intuitive visualization of how different between 2 treatments is. However, to have a conclusion whether the treatment has a statistical effect on survival time or not, we need to perform a statistical test, for example, log-rank test. Therefore, in the next tutorial, we will look into the log-rank test. Hello, this tutorial is about log-rank test. In this tutorial, we learn what a log-rank test is and how it works, or what is its principle. So what is log-rank test? Log-rank test is a statistical method that used to compare whether there are significant differences in survival probabilities between groups or between treatment over time. For example, we can use the log-rank test to compare whether the treatment methods significantly affect the survival time of patients. A log-rank test is a non-parametric test, and it is a type of chi-square test. This is the equation to calculate chi-square, in which G is the number of groups or treatment, I is a group, EI are expected events for group I, and OI are observed events for group I. We will learn more about this equation when we learn how the log-rank test works or how we calculate chi-square for this test. To understand how log-rank test works, we will learn it through an example. The example is the investigation of treatment effect on the survival time of a group of patients. This example we have already used in the previous tutorial, that is Kaplan-Meier curve. The research hypothesis for this study is the treatment methods show difference in survival time. To test this hypothesis, we will test the null hypothesis that states there is no difference in survival time between two treatment methods. Opposite to null hypothesis, the alternative hypothesis states there is difference in the survival time between two treatment methods. This alternative hypothesis corresponds to the research hypothesis. To calculate the chi-square for the log-rank test, we first will calculate expected events. This table on the right are survival time and the number of deaths in the treatment 1 and treatment 2. We need to arrange this data in one table as the table on the left. This table includes survival time, the number of patients dead and alive for treatment 1, and the number of patients dead and alive for treatment 2. T is the survival time. D1 and N1 are the number of deaths and alive in treatment 1, and D2 and N2 are the number of deaths and alive for treatment 2. The sensor data are excluded from the table. As you can see, the sensor data with the plus sign on the right table are removed from the table on the left. As you can see, on the day 1, the number of dead and the number of alive in treatment 1 are 0 and 7, and this value for treatment 2 are 2 and 8. At day 4, the number of dead and the number of patients alive for treatment 1 are 0 and 7, while this value for treatment 2 are 1 and 6. After we arrange the data of two treatments in one table, we can calculate expected event and differences between the observed and expected event at each time point as the table on the right. The question is how we calculate these values. The hazard rate or expected event for group 1 is calculated by this equation, in which N1 and N2 are the number of patients alive in treatment 1 and treatment 2 at each time point, and D1 and D2 are the number of patients died in treatment 1 and treatment 2 at each given time. And this is the equation to calculate the expected event for treatment 2. It is similar to the first equation except for the number of patients alive here. Here is a detail of calculation for the hazard rate or expected event of treatment 1 at day 1, and the result is 0.93. You can easily calculate the expected event for the rest of both treatments. And these are the expected events at different time points for treatment 1 and treatment 2. After you have the expected event, you can calculate the differences between the observed and the expected event as in the last two columns here. When you have all the values, you need to calculate the sum of each column in the table. For the table on the left, you calculate the sum for D1 and D2. Now we can calculate chi-square by replace the sum of expected event and the sum of observed value into the equation. And this equation we have mentioned in the previous section. And this is for the treatment 1 and this is for the treatment 2. And the chi-square equal 4.59. In fact, this numerator for the treatment 1 equals the sum of differences between the observed and the expected for treatment 1. And the numerator for treatment 2 equals the sum of differences between the observed and the expected value for treatment 2. From the calculated value 4.59 and the degree of freedom is 1, you can find the p-value by using chi-square table or using R. The degree of freedom equals the number of groups, that is 2 minus 1, and it equals 1. And the p-value is 0.032 and it is smaller than 0.05. Chi-square can be calculated by using Menzel-Hazer method, and this method is commonly used in the log-rank test. This is the equation to calculate the chi-square value, in which O2 minus E2 is the sum of observed minus expected value for treatment 2, and the denominator is the variance of the sum of observed minus expected. The numerator we knew how to calculate as above, and now we will calculate the denominator. This is the equation to calculate the sum variance of the observed minus expected. Firstly, we need to calculate the variance at each time point, as this example, and then we sum them up. These are the all values of variance at each time point. After we have all these values, we can sum them up and have the total variance. This is the sum of variance, and we also have the sum of the value we have calculated before. Replace the calculated value into the equation. We have the chi-square value of 5.68, and this corresponds to the p-value of 0.017, and this value is smaller than 0.05, so we can conclude that there is significant difference in the hazard rate between two treatments, or we can say survival curves of two treatments are different. This is the result of log-rank test performed in SAS. There are two tables, the summary table on the left and the test table on the right. The summary table shows us the number of groups. There are two groups here, the total observations of each group and both groups, and the number of events and sensor data in each group and in both groups. And here we also have the percentage of sensor data for each group and for all groups. In the test table, you can see chi-square value, degree of freedom, and p-value for the log-rank test, and the other two tests, Wilcoxon and minus log LR. The log-rank test shows the same result as we calculated, that is 0.0171. And this is the result of log-rank test when it is performed in R. The table shows the number of groups. There are two groups here. The number of observations in each group, the number of events or the observed event, and the expected event. We also have the sum square differences between the observed and expected divided by the expected. And the last column is the sum square differences between the observed and the expected divided by the variance between the observed and the expected. And below here is the chi-square value, the degree of freedom, and the p-value. The result obtained from R is similar to manual calculation and also similar to result from analysis using SAS. The p-value here is 0.02. It is rounded of 0.017. We also can visually see the difference between survival probability curves of two treatments, and we can combine the result from the log-rank test with the KM curve. For example, This is a p-value, and this is a Km curve. That's it all for today. I'll see you in the next tutorial. Hello, this section is about Cox regression. In this section, we learn what Cox regression is and how it works, or what its principle is. So far, we have learned Kaplan-Meier or Km curve and log-rank test. Both Km curve and log-rank test are univariate analyses. They can only be used to analyze one risk factor or a single predictor variable. And they can only be used for categorical predictor variable. They cannot be used for continuous predictor. If you want to perform a survival analysis which has multiple predictor variables, or the predictor variables are continuous, you need to use Cox regression. So, what is Cox regression? Cox regression is also known as Cox proportional hazard regression or Cox pH regression. It is a statistical method used to analyze the relationship between survival time and one or more predictor variables. It is a semi-parametric method which makes it fewer assumptions about the distribution of survival times compared to parametric tests. Cox regression can be used for continuous predictor variables, categorical variables, and it can be used to build a prediction model for multiple variables. It models hazard function to predict instantaneous hazard rate at a specific time given that an individual has survived up to that time. This is a formula of Cox regression model. The model is an exponential model and it is based on hazard rate. The dependent variable is hazard rate, or the probability of an event occurring at a given time. X variables in the model are predictor variables, and beta values are estimated coefficients. And H0t is baseline hazard when all the predictor variables equal 0. E power beta are hazard ratios for each predictor variables, and hazard ratio is defined as the ratio an event or outcome happening in one group to that of another group. For example, hazard ratio of death from lung cancer is 2 for smokers, means the chance of an individual dying from lung cancer is twice if he is a smoker compared to non-smoker. Or hazard ratio of death from a group of patients treated by method 2 to patients treated by method 1 is 6, means the chances of a patient dying is 6 times higher if he is treated by treatment 2 compared to a patient treated by treatment 1. So we can say hazard ratio describes the effect of a predictor variable on the outcome, or that is the hazard rate in this case. It is similar to odds ratio in logistic regression and regression coefficient in linear regression. In general, similar to odds ratio, if hazard ratio equals 1, there is no effect or risk of predictor variable on outcome. When hazard ratio is greater than 1, it shows greater risk in the treatment group compared to the control group. While if the hazard ratio is smaller than 1, the treatment group shows less risk than the control group. So Cox regression in survival analysis aims to estimate the hazard ratio for predictor variables of interest. To have a better understanding of Cox regression, we will look at it through an example. The example is to build a model to predict hazard rate of a group of patients based on treatment and their ages. The research hypothesis for this study is treatment method and age can be used to predict the hazard rate for the patient group. To test this hypothesis, we are going to test the null hypothesis, where hazard rate for treatment method and the patient age are equal 0. Opposite to null hypothesis is alternative hypothesis. The alternative hypothesis says hazard rate for treatment method and for patient age are different from 0. This hypothesis corresponds to the research hypothesis. The Cox regression is performed with several assumptions. The first assumption assumes that the hazard ratio of two groups remain constant throughout the following period. The second assumption assumes the survival times of individuals are independent. This means that the survival time of one patient does not depend on the survival time of another. The third assumption assumes that the censoring is uninformative about the outcome of interest. This assumption is satisfied when there is no relationship between the probability of censoring and the event of interest. For example, in clinical trials, we should carefully assess that the loss of flowing up does not depend on the patient's health. We will examine three models. This is a reorganized result of first model analyzed using R. This model has only one predictor variable, 𝐶. The first table shows coefficient, standard error of coefficient, z value, and p-value. The table also includes hazard ratio, and that is an exponent of coefficient, and the confidence interval of hazard ratio. The table also shows the number of patients and the number of events occurring. A p-value is 0.023. It is smaller than 0.05, so treatment method significantly affects hazard rate. The hazard ratio of 6.23 means the treatment method 2 has more than 6 times higher risk than treatment method 1. 2 divided by 1 next to the treatment means that the risk from the treatment 2 is estimated based on the risk from treatment 1. The second table shows the result of global tests including line-loose test, wall test, and score test. All three tests show p-value smaller than 0.05. It means the model is significant. This is the second model. This model has two predictor variables, treatment and age. The second table shows all three tests are significant, so the model is significant. However, the p-value of the treatment is 0.052. It is not significant. Why the age shows a significant effect on the hazard ratio? Although the p-value for treatment is slightly higher than 0.05, the hazard ratio is 6.58, showing that patient treated with the method 2 has a 6.55 times higher risk of death at any time compared to the patient treated with the method 1. Also, the log-rank test in previous tutorials show a significant difference between two treatment methods. So, it is likely that there is a different effect between two treatments. The hazard ratio for age is 1.24, indicating that a patient 1 year older than another patient, but being given the same treatment, has an increased risk of dying by a factor of 1.24. In this case, the confidence interval does not contain 1, indicating the statistical significance of age. This is the last model, the model 3. This model includes the interaction term, and this is the interaction term. The global test showed that the model is significant. However, no significance was observed for treatment, age, as well as interaction. Because there is no significant interaction between treatment and age, we should not include the interaction in the model. That means we should use the model 2 for prediction. The model 2 we have already discussed previously. This is the last tutorial for survival analysis. I hope you enjoy my lectures. See you next time. Thank you.